Today's lecture is the final lecture in the series on statistical evaluation of good, reliable, responsible data. And we will talk about the two-way analysis of variance in this lecture. And I'll switch over to the slide set now and begin this slideshow. So it's Module 2. Again, we're completing the research, design, and data management, at least as it was established at the time of recording this file. Might be changed in the future, so don't be shocked if indeed it does. This is the Lecture 10, the two-way analysis of variance, and then we'll spend some time on the non-parametric analysis of variance tests. Again, we said that we would see this flow chart for choosing an appropriate statistical test repeatedly, and what we are following through with in this lecture, of course, still with continuous data that's normally distributed, more than 2 treatment groups with equal variances, the analysis of variance, but of a slightly different structure, the experimental design leading into it, therefore different and slightly more complex calculations. We won't go through all the formula for that, the two-way ANOVA in this case. And then also we'll spend a little bit of time for the non-parametric analyses. Actually, I'll just be doing the two-way ANOVA for the ordinal, the Kruskal-Wallis test. So we won't be using any of these others as an example, just the Kruskal-Wallis. And I'll show how that type of data for non-parametric data that uses different measures of central tendency and dispersion around that central tendency in the graphical display. So the two-way ANOVA, we remember our one-way layout. It's one factor but more than 2 groups. Now it can be the repeated measures, a paired type of a study. But it's one factor with multiple levels and more than 2 groups. So that makes it a one-way layout. The two-way layout obviously is going to have 2 factors, each factor at different levels. So we'll go through, see a couple of examples, and see if we recognize whether it's been approaches appropriate. And I hope that once you complete these studies, you can recognize experimental designs and question, be critical of the statistical analyses that were used. So we want to be 2-part. We want to know how to design experiments and have them designed so that the appropriate statistical analysis is run on them. We also want to be able to do the reverse, to look at the experimental design and determine if someone has used an appropriate or inappropriate statistical approach to evaluate the data. And obviously you can't draw conclusions on faulty statistical analyses, and that's what's so important. You can make observations, have bar graphs where they look different, and say, you know, increased, and make all these conclusions and try to fit it back into the theoretical framework, and it is all without the correct experimental design, of course, but statistical test, it's useless. Absolutely unacceptable in science. So the term one way means that the subjects are categorized in one way. The two-way ANOVA, the subjects are simultaneously categorized in 2 ways. So for an example, you might study a response to 3 different drugs in both men and women. So we have one factor that's just categorical, but the other factor that would be some numerical distinction. Just completed a two-way analysis in the laboratory before coming to give this lecture, looking at the effect of a 0 concentration and a 10 milligram per kilogram concentration of a drug in 3 different age groups of animals. So got 2 factors, drug and age, and 2 levels for factor 1, drug, and 3 levels for the age. So it should be very obvious when those are two-way analyses. So obviously age, I can put a number to it, but it's young, middle, and aged. It isn't a continuous data set of every age possible. So that should be obvious to you as a two-way analysis of variance. So each subject is categorized in two ways, by gender and by which drug he or she received. And in the case that I just described, it was 3 different ages. Each animal of each age group was animals in each of the age groups were split into 2 groups, were exposed to either of 2 levels of the same drug. But they were paired by criteria, age and strain and gender, before the experiment started. Remember, we said that last time, that if you're going to do a paired comparison like repeated measures, you have to be sure to pair things to begin with. So it's really controlling the bias as well. So because it simultaneously asks 3 questions about and computes 3 p-values, so there's interaction, first factor, and second factor. So we recognize first factor, different levels, second factor, different levels, but this new term, the interaction, is what we want to begin to get a feeling for. So the interaction is taken from the approach that the null hypothesis. So remember, a statistical test, as we're seeing in these studies, is always testing an hypothesis. Right, a statistical hypothesis. Remember, way back we distinguished between statistical hypothesis, the null and the alternative hypothesis, from our scientific hypothesis. But in essence, after completing our testing of the statistical hypotheses, we have determined if our data is statistically significant and supports or does not support our scientific hypothesis. So we're testing the null hypothesis that there is no interaction between the factors. So in the case of the study that I just told you I completed my analysis on, I actually had significant effect of age and interaction. So I have to go and try to figure that out when I was expecting a significant effect of the drug and a significant effect of age, as well as probably an interaction. So I've got to evaluate it. It may be that the drug had an effect only at one age, and therefore it's not a significant effect of the drug, but it is a significant effect of age, and therefore interaction, because the animals had to reach a certain age before there was an effect. And still just the same, if on one of these 3 we pass the 2-way ANOVA, then we are given permission, if you will, to go on to the post hoc analysis. So for the interaction, we're saying that there is no interaction. So the drugs, in our example, the null hypothesis is that the difference in effect between men and women is the same for all the drugs. So there's no difference in the magnitude of effect between the genders, is the null hypothesis. The p-value answers this question. If the null hypothesis is true, what is the chance that randomly sampled subjects would show as much or more interaction than you have observed? So if the interaction is statistically significant, you will usually find it quite difficult to interpret the individual p-values for each factor. So that's what I was saying, is I've got a significant interaction and a significant effect of age, but not of the drug. So I've got to work on it, take some creativity and thought and review of the literature to understand what that means. The first factor, the null hypothesis, is that the population means are identical for each category of the first factor. So again, it's that there's no difference between the mu's. In our example, the null hypothesis is that the mean response is the same for each drug in the overall population, and that all observed differences are due to chance. So again, if we get a significant P, we reject the null hypothesis and accept the alternative hypothesis that at least one of the effects must be different based upon the first factor. In this case, the first factor was drug. And as you recall, it was the same with mine. I didn't get a significant P. I have to accept the null hypothesis and assume that the responses were all the same. So it gets pretty tricky. The second factor is gender in our example. The null hypothesis is that the population means are identical for each category of the second factor, or each level of the second factor. In our example, the null hypothesis is that the mean response is the same for men and women in the overall population, and that all observed differences are due to chance. So the p-value answers this question. If the null hypothesis is true, you randomly select subjects. What is the chance of obtaining means as different or more so than you observed? Well, let's take a quick look at some of the formula for this. And as I said, we're not going to get into all of them for the two-way NOVA. You're welcome to visit a stats textbook if you need. Again, as long as you know you've got your data set up, and I'm going to bring the PIP back in for this, I just spent the majority of my time determining how within my software package do I have to organize, and of course went to the help to look for it, how do I organize my data table to feed my numbers into the statistical package. Now we'll look at a two-way NOVA data table in just a moment, and your software package may or may not have the numbers input in that same fashion. Still the data is organized and separated in a similar fashion, but it may differ a little bit. So do you put your numbers within each group in rows or in columns? If they're in columns, how do you organize it? How do you tell it that, you know, the this level of this factor ends here, and then the next level picks up and takes it on from there? So it gets pretty tricky. You need to become familiar with how the data needs to be set up and how your software package is going to accept it. So here we see the three hypotheses tested are as follows. The null hypothesis prime, alpha 1 equals alpha 2 equals so on and so forth equals 0. So we're saying that none of them is different from 0. So the alternative hypothesis is that at least one of the alpha i's, alpha L to I here, of course, is not equal to 0. And then the second hypothesis is focusing on the betas. We see our type of errors coming out here. At least one of the betas is not equal to 0, and then finally it's the alpha beta, and at least one is not equal to 0. So we see there's a calculation of mu's that take into account the alpha and beta separately and then collectively, and then another, the observation I, J, K equaling this for the sample set. So it gets very complicated. It may not be impossible for you to pull out the formula and do all these calculations. Most people, as you know, are using statistical packages. Some of the scientists I know, before they will trust completely a statistical package, they have someone in their research laboratory, typically a student or a technical person, take the data and do all the mathematical calculations by hand, and then compare that result with the that produced by the statistical package. So remember, all of this was done by hand, maybe with a handheld calculator, but it was all done by hand before all these software packages came around. So unless you have a truly validated software package, you may yourself, under some situations, validate it before begin using it routinely. So here's the organization of the two-way data table, two-way classification with several observations per cell is the terminology for this. So we have rows and columns, and you see that there's 1, 2, out to the R levels for the rows, and 1, 2 out to the C levels for the columns. And it is set up with got to get a little closer here on this, X1, 1, 1 down to XR, IX. So this is observation 1, column 1, row 1 here. See, and this is the unique identification of a data point that the software package must be able to determine. Now, I've worked with some software packages where you have to tell it, and it has to be an identical number of observations, as we see over here in the example. There are 3 observations in each group. Therefore, the program knows to go down 3 rows within a column, and that's one treatment group. The treatment 1, level 1, treatment 1, level 1, whichever treatment you want to call. Treatment 1, level 1, treatment 2, level 1. And this is the designation, so it's the observed data point at column 1, row 1, and it is the first observation there. So the only number that changes in the next one is the last number, because it's still the 1, 1 level, the first level for row and column, but it's the second observation out to the N for that group. And we see that the calculations, there's totals and means for each, and then there's a total for each row, across the columns. Sorry about that. Across the columns, there's totals and means, and then for each down the rows, there's a total and a mean as well. So across the rows and across the columns is the way that we want to think about that. Now we have to keep this picture of the data in our mind. There are little pockets or cells. So here's a cell, in our sample data, here's a cell, and here's a cell. So within a cell, there's a cluster of data points for a particular level of a treatment, 1 and 2. And so this is how you need to visualize this in your mind, because if you can visualize the data set, I always tell people that try to visualize your data set and visualize what your graph will look like first, and then work backwards to see what is the layout of your experiment, what statistical analysis do you need to use to study it. If you're struggling with it a little bit, start with the way you'd expect your data to look like on a graph, and then work it back to a data table, and then determine the layout, and then you're at the statistics. So the two-way classified data, since there are MN levels for the 2 treatments, that sounds familiar from the one-way ANOVA, and P observations per treatment, there would be MNP observations in all. So it's a similar type of statistical, mathematical textbook writing that we all enjoy so much, I'm sure. But it is making the point that you have 2 levels and a number of observations in each level. Since neither the observations in a single row nor those in a single column can be rearranged, the objects are said to be classified in 2 ways. So in this one, we can't rearrange the numbers in the row anywhere, In the one-way layout, we could take, the rows within a column could be rearranged in any way because they're all data points from the same group. But we couldn't just take a data point in a row from one column to the next column because it would affect the means as we had described. In the case of the two-way, you can't move numbers anywhere. Of course, within each group, maybe you could if you're thinking that, but the way we have to think of it is all the rows, let's go back to our data table, all of these rows within a column, we don't have the freedom to move this number up there and that number down here and that number down there and that one up there. We can't just move them around without impacting the mean within each cell. And we obviously can't take this and put it there and this and put it over here. So we're locked in. The numbers have to be put in a very strict fashion. They have to be clustered into these cells. It's in fact flexible, so it is a two-way classification. So here's a result table, the analysis of variance for the two-way classification with interaction. We look at the source of variation, can be the row means, the column means, or the interaction. And then there is an additional one. This is that residual that we've been putting off. It is an error. So there's the sum of squares for each, degrees of freedom for each, and then of course there's the total as well. And then mean square, and then the computed f. Remember, the f value is always a ratio taking into account the variances. So the f1 is this variance ratio, f2 and f3 are three hypotheses. We get an f value for each, and it's the same. The observed f value has to exceed the critical f value, so that wording is consistent. The statistical approach is always the same. There just might be some slight modifications in the formula for getting the critical test statistic value or calculated or observed, and also comparing it to the critical. So note that there's a between rows and between columns and a residual sum of squares here that equals the total sum of squares. So here's an example of a data set, again with the GraphPad Prism. This was actually the version 2. I'm now up to the version 4. The version 2 allowed a two-way ANOVA, but not a two-way ANOVA repeated measures. So this is what we're doing. So here's the data set. You can see that this is for rats that are behaving. It's a self-administration. So this is the table, the self-administrative active level table for the ANOVA. So it's laid out for the ANOVA. We don't have the far left to show, but these are different time points. And so you should begin asking yourself whether it's a repeated measures or just a two-way ANOVA. Anyway, these are different time points that are being measured, and then this is all the observations, 12 individual animals, 12 observations in this set for an RD1, and there's various columns like this with all these replicates within there. The next thing that you're prompted to put in are the two variable names, the two factors. So those drug and time were the two factors, as I had indicated. And so hopefully already you're realizing that because the software wouldn't let me do repeated measures, the wrong statistical analysis was applied to this data set. If you measure in the same animals over time, which in this case it was, lever presses over time, that's a repeated measures. Now, we'd have to look at the design differently where there are two factors otherwise at more than one level for each factor that were also tested to make it a two-way. This may actually be a one-way repeated measures ANOVA, depending upon the overall design of the experiment. It was just a set of data that I had that I could structure to do a two-way ANOVA on this, but it's kind of a good exercise where already you should realize this is probably an inappropriate statistical analysis for this type of data set. But it gave us some values anyway, and this is why I say you need to know what you're doing with your software package, because you can get results and you can go and interpret it and report it, and unless there's someone in the audience, either the readership audience or actual audience viewing it, listening to you, unless there's someone in that audience that is astute to statistical methods, they'll believe what you're saying, because you're saying you got a significant ANOVA at this value, that you report the F value and everything, and then you go on to the post hoc comparisons, and you're showing graphs, everything looks like it should be significantly different. But if you put the numbers in wrong or run them through the wrong test, you can get significant p-values that are not appropriate. And if you get called on it, it certainly would be extremely embarrassing. So I'm not embarrassed now because I did it on purpose, because it was the only data set I had at the time preparing this lecture to do the analysis. Now I'm glad it's there because I'm able to make this other point. So here's the typical outcome that you get: interaction, drug, and time, the factor 1 and factor 2. You get the percent of the variation for each of them in this case, and you get a p-value. In this case, all three were significant at p less than 0.0001. The source of variation, we see the p-value summary. So we said 3 asterisks are p less than 0.001. 1 asterisk is 0.5, 2 asterisks is 0.1, and 3 asterisks is 0.01. So each was a significant source of variation. And then we see for each of these sources of variation, now adding in the residual, we have the degrees of freedom, the sum of squares, the mean squares, and the F value. So we would say that the two-way ANOVA was significant for the effective drug. I'll just do that in this case. And F, open parentheses, the degrees of freedom for that treatment, and then the residual. So it's not the total degrees of freedom, as we saw with the one-way ANOVA. When you report your F value for a two-way ANOVA, the second number in the parentheses just after your F is the 1650. I'm going to switch to document camera. I've said this a zillion times, but I've never written it out. So within the text, you say the two-way ANOVA was significant for the drug, the effective drug. And then in the bracket, you put F, open parentheses. It was degrees of freedom for that treatment were 9. And degrees of freedom for the residual was 1,650. Remember, one-way ANOVA, this is total degrees of freedom. For the two-way ANOVA, it's the residual. And that equals the F value for drug was 133. And that was at a p less than, remember our 3 asterisks, 0.001, and we close the brackets. That's how you report your ANOVA values within the text of your results. This would be, of course, for the two-way. And it would be reported for each of them. Since all three were significant, you would have to state that. The two-way ANOVA was significant for drug, and then give your F value in the format it did. And then you might put a semicolon, time, you do the same, and then interaction. And of course, if you stated that you used a two-way ANOVA, but not a repeated measures, and you report it this way, where you've got drug, time, and interaction, anyone should be able to jump on that immediately and say, you did the wrong statistical test. The way that it looks here with the two factors you put in, that should be a one-way ANOVA with repeated measures on time. So that's why it's important to recognize what all this means, and that's why it's critical to report your F values when you do the analysis of variance, so that the reader knows that the data is legitimate. Because anybody can drop numbers into a spreadsheet and bring that into their statistical analysis package, and if they're not organized correctly, they can get any kind of a number. Now, of course, from that as well, I didn't show you, there should be the tabular output that would have the mean and the standard error of the mean and the standard deviation and the range of your data points, the minimum and the maximum for all of your groups. And those should match what you have calculated in a spreadsheet otherwise. So you must calculate your descriptive statistics in a separate spreadsheet if you were going to run them through your statistical package. Now, most of the statistical software packages that I've seen don't always let you take the data from your two-way ANOVA straight into a post hoc test. The reason for that is the data is not organized the way that the post hoc tests are accustomed to evaluating them. So at least in this one, what you have to do is have your data organized differently, a separate column for each treatment group at each level, level 1 and level 2. So you got to force it into a one-way layout, run a one-way ANOVA on it, discard that, it doesn't mean anything, and then it'll run the post hoc analysis to compare all your treatment groups. So you need to become familiarized with how your software package will take your two-way ANOVA data and feed it into or through your post hoc analysis. Some may be a bit more sophisticated and are programmed to do it both ways. As I said, this one that I use, I just discovered, and actually it was the way that software packages were back when we were working in DOS, and things weren't so nice and convenient as they are in Windows. I realized that you could do your two-way ANOVA, but you had to have your data set up in a one-way table and the software was just set up where you had to run the one-way ANOVA, and then it would automatically do your post hoc analysis. So you did a two-way. If that was good, you organized your data to do a one-way just to get your results for your post hoc test. So you need to become familiar with how your software package does the post hoc follow-up test subsequent to satisfying or passing the requirement for the ANOVA. So the ANOVA table breaks down the overall variability between the measurements expressed as the sum of squares into the 4 components. Interaction, the between row and column, variation between rows that is not the same for each column, or equivalently, the variation between columns that is not the same for each row. And then there's a systematic variation between the columns, a systematic variation between the rows, and again, what we're beginning to evaluate here, it may not come out, that clearly, but we can picture our data table. We must have a source of variation across the levels. We must have a feeling for the estimation of variation within each cell that must be minimal compared to the variation we get across the levels of each of our treatment factors. And in the example we're using, we had two different drugs, I guess, and two genders. So one of those test factors with its levels should generate a variance that exceeds all the other variances, and then you'd say, well, there's an effective drug, but not an effective gender. And if the gender produced a variance as well, then you'd obviously be questioning whether there was a difference based upon gender. And the variance from looking at each of those as you go through the different cells for the different treatment, the different levels for each factor, kind of a correlation type thing again, is the interaction. So remember that the interaction we can interpret as a test for the correlation between the two factors. Now there are two factors at the different levels. So there's something going on where each factor is not acting independently from the other factor at each of the levels. So you have to begin to interpret it from that perspective first. They're not acting independently. There's something about one of the levels at least of one of the factors that's causing one of the levels at least of the other factor to produce an effect that is different. So in essence, that's the the interaction. It is a lot easier to interpret your data if your two factors, or one of the factors is significant with the two-way ANOVA, but you don't have a significant interaction. It's much easier to interpret. And then there's the residual or the error. So it's the variation among replicates not related to systematic differences between the rows and the columns. So it's just an overall feel for how much variation there is in the entire data set. Is there a source of error in the entire data set that just can't be explained? Now that's not very mathematical, I know, but it's the best I can give you for understanding the residual. Statistician or intermediate or advanced level statistics textbook both are available, of course, and hopefully they would be able to provide a more satisfying explanation for you than I may have been able to provide. Continuing with the ANOVA table, it shows the degrees of freedom and the mean square for each component, as well as the F ratio. Each factor ratio is the ratio of the mean square value of the residual mean square. Did that make any sense? I don't know. I was reading it and not thinking about it, but I'm not sure it made any sense. Anyway, if the null hypothesis is true, the F ratio is likely to be closer to 1. If the null hypothesis is not true, the F ratio is likely to be greater than 1. So this should begin to make sense as we remember that the variances are being used for the ratios. So if the null hypothesis is not true, you have a source of variance that is exceeding the residual variance, and it should exceed 1, meaning that there's some source of variance for the interaction or treatment factor 1 or treatment factor 2, because remember, all three of those F ratios were calculated, that indicates a difference exists, a statistically significant difference exists. So, see any statistics book for help for interpreting the table. Most scientists will skip over the ANOVA table and focus on the test of the three null hypotheses. we may find that to be true, but depending upon the type of research setting that you are in, you will need to be ready to defend the statistics at different levels. And of course, you need to develop a confidence within yourself to meet the demands for whatever type of research setting you're working in. So here's an explanation for that. You can see there's this interpret button here on this version. It provides an interpretation of that. So it shows the source of variation, the degrees of freedom, the sum of squares, the mean squares. Does the drug have the same effect at all the values of time? Interaction accounts for about 34.28% of the total variance. Here's the F, 13.2 degrees of freedom for that, for the interaction, and the degrees of freedom residual. The p-value is less than 0.001. So this is what I was saying, except you just you don't write it out like this. There's the abbreviated form, F open parentheses 126, comma 1650, close parentheses equals 1320, semicolon, p less than 0.0001. So that's where there is. If there is no interaction overall, there is less than a 0.01%, convert this to percent, chance of randomly observing so much interaction in an experiment of this size. Remember, size was important. If you get too large, then you can get really significant effects that might not be real. The interaction is considered extremely significant. Since the interaction is statistically significant in this case, the p-values that follow for the row and column effects are difficult to interpret. So does drug affect the results? Are the curves different? The drug accounts for 24.66% of the total variance. The F is reported. It's the same as how we had reported it. We use the same numbers. If drug has no effect overall, there is a less than 0.01% chance of randomly observing an effect this big or bigger in an experiment of this size. The effect is considered extremely significant. And same thing, of course, for the factor of time. So interpreting the results of the two-way ANOVA, because the two-way ANOVA simultaneously addresses the three questions, the three hypotheses, the results can be difficult to interpret. So for more details, we recall that it tests the three null hypothesis, the interpreting of the p-values, and the ANOVA table. So how the two-way ANOVA works, it partitions the overall variance of the outcome variable into four parts. Some variance is explained by systematic differences between columns. In the example, some variance is explained by the difference between drugs. Some variance is explained by systematic differences between the rows. In the example, some variance is explained by the difference between men and women. In the present case, differences between the time points for the one that I ran that was wrong there, but produced some numbers and statistical tables for us. Some variance is explained by an interaction between rows and columns. This means that some variance is explained because the difference between rows is not the same for all the columns, and the difference between the columns is not the same for all the rows. In the example, some variance is explained because the differences between men and women is not consistent for all drugs. And the one that I just showed you, you'll see there'll be some up and down as we go through time, and that's what created the interaction. So the rest of the variance is due to scatter within the groups not related to systematic differences between rows and columns. This is called residual variance or error variance, and that was that residual that we've seen all along. There's some residual variance just within the collective data set that needs to be taken into account but isn't explained for within the mathematical analysis. Accounted for, excuse me, that isn't accounted for in the mathematical analysis. The ANOVA calculations compare each of the first three sources of variance with the residual variance. So the p-value, and that's why you report the degrees of freedom for that test factor or interaction with the residual degrees of freedom for the residual variance. The p-value is based on this comparison, adjusting for the number of rows and columns and the number of replicates. As with the one-way ANOVA, special methods have been developed to calculate post-tests, focusing on particular differences. The methods have also been developed to deal with the repeated measures. So here's some of the data graphical data that we ran through the two-way ANOVA. So you can see there are many different individual animals, and these are the data groups for different days for the animals. In this case, they self-administered 30 milligram per ml. It was amphetamine, and this is the group that administered the ringers. So we measured this same data set. It was in essence paired ringers groups with these on each day. So 2 levels of the drug, 0 and 30, and then the 5 levels of the second measure, second factor, which we said is wrong. It should be a one-way with repeated measures. But anyway, that's why we fed it through. But here you can just see the data is up and down and different across all the days. And so in any one day, you try to compare between the ringers and the amphetamine. It becomes quite difficult. So there's some type of interaction going on, meaning that it's not always having the same effect on the same day for each of the treatment groups. So this is that same data table that we saw before. Remember this type of evaluation. So we look at variance in this way, and we look at variance in this way, and try to determine if these sources of variances could be significant and help us to understand if there's an effect of factor 1 at the different levels or effect of factor 2 at the different levels. But then how about coming across this way? So how's this group to that group, to that group, to that group, or cell I should be saying, right? These are our cells of data. And that you can kind of see, that's like a correlational analysis. You're correlating the change of this with the change in that. And that's the interaction. So these next couple slides are on the repeated measures. I repeated the same slides. Again, at the time of preparing this, I didn't have the new version, so hopefully sometime in the future I can update the slide set and provide the information on the repeated measures for the two-way, but it's the same thing. You're now proceeding to a paired test, even though you're doing a paired analysis. Excuse me, even though you're doing a two-way ANOVA. So these are the exact same slides from the previous lecture on the repeated measures ANOVA. And this was the one-way ANOVA on this particular data set, the way it should have been run, setting it up for repeated measures ANOVA, the one-way, Newman-Cool's post hoc test, went with that rather than the Tukey's. Here's Bonferroni correction for multiple comparisons and the Dunnett's test, so the choices are there. Newman-Cool's is a standard that I have used. This was another software package. I just couldn't figure out how to use it. Found one that I liked better and stuck with that. This is NCSS statistical package. So if your data was in here in the appropriate way, you'd select ANOVA. You'd have analysis of variance, GLM ANOVA, whatever that is, nonlinear models, MANOVA, one-way ANOVA, repeated measures ANOVA. So I didn't really like this one so much, but here we see the repeated measures ANOVA. It seemed only to allow the one-way ANOVA, and all these other things, response variables, between factor, the between factor 2, factor 1, factor 2, factor 3. So it seemed that if you could fill in multiple factors, it would either do a two-way or a multiple factor analysis. I struggled with it for a while. Most of my experiments didn't become this complicated. Didn't find the help to be quite so helpful. Even had a few other people take a look at it and try to use it for their work, and they didn't like it either. So it came with this PAS6 navigator that also had a power analysis component. And for comparing means, you could had many more options to feed in information, whether it's repeated measures ANOVA, regression, correlation, proportion, and things like that. So I did like it for that, but ran out of time for the test version of it and decided not to buy it, and so I didn't have a chance to finish using it for a demonstration here. But it does show that software packages are available to do your power analyses for all these types of tests and the estimation of your sample sizes. The ones that we use, remember, were only appropriate for the student t-test, comparing two experimental groups that were actually unpaired. So now we want to do a little bit about the non-parametric tests, and this is where we're going to talk about the Kruskal-Wallis, which is the equivalent to non-parametric one-way ANOVA, actually. So if you're unable to assume the data are sampled from a Gaussian population, then you calculate the p-value using the non-parametric test. So you test analogous, this test is analogous to one-way the Kruskal-Wallis test is. The test analogous to the repeated measures one-way ANOVA is the Friedman's test. Like the Mann-Whitney test, these tests first rank the data from low to high and then analyze the distribution of ranks among the groups. So remember, with the non-parametric, our measure of central tendency is what? That's right, the median, and the estimate of dispersion of data around the central tendency is going to be quartiles or percentiles. In this case, it'll be quartiles, as we'll see. So the Kruskal-Wallis statistic first ranks all of the values from low to high, regardless of the group, sums the ranks in each group. If the sums are different, the p-value will be small. The program reports the Kruskal-Wallis statistic, which is computed from the sums of the ranks and the sample sizes. So we don't go through all the mathematical formula for this. It's more of just to appreciate how it is approached. It's more of a ranking and looking at the median value. So this test assumes that the data are representative of a population. Remember, we're always worried about that. Each subject for each experimental unit was selected independently. Again, this is one of the assumptions of the independence of our data points. The populations don't need to follow a Gaussian distribution, but the populations themselves should have distributions about the same shape. Maybe not on that outcome variable that you're considering with this statistical test, but it should be a normal population, right? And the sample should represent that. The Kruskal-Wallis test is a non-parametric test to compare 3 or more unpaired groups. So again, that's the same as the one-way ANOVA. The p-value answers this question. If the populations really have the same median, what is the chance that random sampling would result in medians as far apart or more so than observed in the experiment? So the effect size, what is the magnitude of the effect? The p-value, if your samples are small, PRISM calculates an exact p-value. If they're large, calculates the p-value from a Gaussian approximation. The term Gaussian has to do with the distribution of the sum of ranks and does not imply that your data need to follow the Gaussian distribution. So I guess Gaussian did more work than just the normal distribution, right? With medium-sized samples, this software package, the GraphPad Prism, can take a long time to calculate the exact p-value. You can interrupt the calculations if an approximate p-value is close enough. There are faster computers nowadays, so that's a little bit less of a concern. So here's a data set from work that we did looking at the diameter of rough endoplasmic reticulum in response to a neurotoxin combined with microwave exposure. And we determined that it was, we categorized or we classified the proportion of cells in each treatment group of affected and not affected, forcing us to go with non-parametric. So we went with a non-parametric analysis of this. Even though it's continuous data, we are forced into a complete non-parametric analysis. So the Kruskal-Wallis test gave a significant p-value, less than 0.0001. Exact or approximate p-value was a Gaussian approximation. Here again are 3 asterisks for 0.00. Well, I'd put 4 asterisks because it's 0.001. Do the means vary significantly? Yes. The number of groups were 6. The Kruskal-Wallis, again, a critical test statistic is calculated. The observed, 219.9. And then a Dunn's multiple comparison test was the post hoc test that was used, and we see all the comparisons, individual comparisons here. The p-values given, and of course the summaries given here. This is that comparison shown on a separate page. So here's where you'd look to see, if the vehicle group versus, let's do the vehicle plus the highest, the drug treatment plus the highest level of microwave, it was significant at p less than 0.001. And then the column statistics are calculated as well. So in this case, the median and the 25th percentile, this is the first quartile, and the 75th percentile, the third quartile, is what we will see will be used for the graphical analysis. And we'll look at that and evaluate it in just a moment. So for the non-parametric, it's the median and the first quartile and the third quartile that become important. The quartiles represent the dispersion around the mean, around the median, which is the measure of central tendency in this case. Now the mean, standard deviation, and standard error are also calculated so that those can be evaluated, but they are not appropriate for reporting non-parametric data. You report the median and plus or minus the first quartile. So when it comes time to display non-parametric data graphically, it's the box and whisker that are box and whisker type of graphical display that is used, and that's what's shown here on this slide. So it is the median plus or minus the first quartile, 25th percentile, plus you have the 95th percent confidence interval. And so what you see is that in some cases it's pretty balanced, but in other cases the median, and again you've got the median here, so is the magnitude of the effect or the effect size big enough here, but your quartiles are overlapping and your confidence interval in this particular treatment group is pretty high. So what is actually happening there? Might it be significant or is it not significant? And of course we'd come back to this. That was the vehicle versus this one here, and it was statistically a significant difference, although that must be based upon the magnitude of the effect size based upon the median. If we take a look at the mean and the standard error of the mean, the typical bar chart that we'd see, here is that group. So we're comparing back to the 0, 0. With the standard error of the mean, we see visually that that shows a difference as well. So this is likely to be true. But what we see is that more of the data points are distributed in the first quartile below the median than above the median. That's how we interpret that quartile. And if we look at this case here, more of the data points are distributed in the first quartile above the mean than below, and it's even more exaggerated in this treatment group here. And we see when the two are combined, it creates a data set, the median and the quartiles and the 95th percent confidence intervals that is set aside from all of the rest. So there's something distinct about this, and we see, actually, if we superimpose these graphs, we see that there isn't a big difference between them. It's just that if you do non-parametric analysis, the box and whisker with the median, first percentile, plus and minus, as well as plus and minus the 95th confidence interval, is the accepted means for displaying that data. Most of us are accustomed to seeing data this way. So again, that brings us back to this flow chart. We have spent some time on at least the parametric and non-parametric and discussed most everything that's on here. For non-parametric, we just did the one example of the equivalent of the one-way ANOVA with the repeated measures. And there are others here if the data is paired, but we're not going to do examples of that. So this completes our discussion of the statistics on the Module 2, Lecture 10. I appreciate your time and attention, and hope you have gained a better understanding of the interrelationship between statistical analyses and experimental design. If you remember way back early, we had objectives, design, and statistics, the analysis, and there was always the one-to-one interrelationship back and forth. Well, now we have completed that discussion of each of those, the research objectives, the design, and the data analysis. So I'll leave the rest to you to become an expert in statistics as you continue through your career in research science.